Welcome to Drone Systems and Control course. In the previous lecture we talked about swarm technology, challenges in swarm technology, right, like uncertainty in sensor, uncertainty in computation, uncertainty in communication, uncertainty in decision and actuation challenges. And these swarm of drones are deployed to handle problems where the region is also uncertain. It's like forest fire, or you have a problem of search and rescue, where the survivors are, where the targets are, how many targets are, those are unknown, they are uncertain. When you have those kind of a problem, swarm UAV based solutions are most suitable. Try to give a connections. We talked, the whole course is about single drone, right, and their autonomy aspect of it. But that alone is not sufficient for many practical problems. Problems like perimeter defense, problems like cooperative payload transfer, where group autonomy have to come into picture. Many drones have to cooperate among each other. Right? That's why we talked about the swarm as one lecture, so that you can appreciate. Right? And we discussed about perimeter defense as one of the problem, right, where we made certain assumptions and we created a formulation and show some solutions. But that has its own assumptions to be taken care. Right? The incoming intruders could be cooperative and intelligent too, and highly maneuverable. When you have such kind of situation, your defenders have to be more intelligent, more cooperative to protect your territory, right. So that's the interesting problem space one can look at it and work. And this particular lecture we talk about firefighting, right, how the multiple swarm of UAV. See, in the previous one we talked about drones which are in the perimeter, they are not a swarm, right, whereas here we are going to talk about multiple swarm. The problem what we are addressing here is there is a large area, right, when you talk about forests. In India we have quite a lot of such problems are there, right. So in summer, northern part of India, in southern part of India also, forest fires are quite common because of the dryness, right, and heat. The forest catches fire all the time. The challenge there is it's very difficult to approach that location. The terrain is not going to be smooth, right. There is no road. That's where the complexity increases. By the time you detect, they start spreading from one location to another location. The size of the fire defines the number of drones required to operate, right, to quench. Not just only on the number of drones, it also depends on how much resources these drones have, right. So it's a very interesting problem again for a group autonomy to come into picture. So we thought we'll just give you an introduction to it. If you see here, the large area of fire, right, I am putting 3 swarms here, and 3 swarms are just searching for it. Once they detect, they work together and quench. Suppose the fire is so big, these swarms merge together, right, and quench, and they move out and keep searching, right. It's a very interesting problem space. What we are saying, we know the boundary, the region where the fire could be, which is known, okay, and how many swarms are there, and each swarm, how many drones are there, which is also known, right. What we don't know, the location of the fire, and what is the spread of this fire, which is unknown for us. The swarms, they will fly within the radius. That radius is highlighted in the red color for you to understand. They can go in any heading, but they will be within that circle so that they can talk to each other, right. That's a swarm behavior. And we are talking about dynamic multiple swarms. So there are multiple swarms Why dynamic? Here the swarm can merge and split based on the requirement. Unfortunately, in this particular GIF file I showed 2, right. You can't split. If you moment you split, that will become single UAV, that is a distributed UAV kind of scenario. So, there is no split here, right. They have to merge together, they have to repel each other based on the situation. Suppose there is a task. The task can be executed by a single swarm and another swarm is approaching, then this swarm should repel that particular swarm. When there is a task which requires more than one swarm to operate, then they need to attract, right, they need to merge, right. So, they have to regulate the number of UAV based on the problem space that they are operating, right. They have to be cooperative, they are all information driven in that particular scenario. So, fire mitigation again within the swarm, when they are trying to mitigate, they do divide and distributed rule. What is divide and distributed rule? No two swarm will spray water on the same location, they divide the whole area and distribute among themselves so that they approach the task in their own region, right. Now, what are the challenges here? If I talk about forest fire, the location, the number of fires are unknown, the fire is not constant. What I meant is not constant, the area of fire is not constant, they are growing with respect to time. Now again, how they spread depends on the wind, depends on the carbon content, depends on the moisture present, right. If the moisture is high, it won't spread in that location. If the moisture is less, it is dry, it spread in that area. But it is very difficult to find out how they spread because we do not know the carbon content. To make our life easier, I assume that the carbon contents are uniform, all of them are dry, so that it is easy for them to capture, which means the fire always spread in uniformly all around and there is no wind. If there is a wind, the spread will be in the wind direction, right. I am assuming there is no wind. We can relax one by one, right. Now quenching, I am assuming that the carbon they are capture the once it catch fire, it will go to maximum intensity, right. To quench that I need certain critical flow. I know the carbon content, so I know what is the critical flow of liquid required to quench the fire. The rate of quenching will not increase if you increase the flow beyond certain point. If you pour water, let us say, if you pour more water, it is not going to quench faster. Okay. So, there is a limit the maximum UAV for quenching. That means you can't have more number of UAV just to quench that, right. That is a philosophy. The second thing is the UAV should be there so that they do not collide with each other, right. Quenching time depends on the area, detection time, quench rate, the number of UAV, at what time the UAVs are joining to quench the fire, that will also affect. So, I can what is that I want to minimize? I want to minimize loss of damage, loss of biodiversity, right. I do not want the many regions to be catching fire, losing carbon content. I want to minimize the time to quench, which will also reduce the loss, right. I want to detect before the fire is uncontrollable, right. I have only 10 swarms and if the fire is so big only 10 cannot handle, then it is a problem. So, I have to detect the fires as early as possible so that I can quench before it is creating a larger damage. So, that is a requirement. So, if you look at detection is also important, right. Detecting large fire early is better so that I can just control it. Detecting large fire means I can't ignore the small fire because by the time small fire become a large fire, right. So, it is like a multi-objective problem to minimize so that the overall loss can be taken care of, right. Now, let us look at the UAV. Each UAV has a sensing radius, right. within the sensing radius, their detecting ability is more like a Gaussian in nature, which means they have a high probability of detecting when they are right on top of the target. The probability of detection decreases when the target is present away from the sensor, right. Beyond the sensing radius, my detection probability is 0, right. I am defining a large swarm boundary and with the center, swarm center and radius. So, I can get this information because they can talk to each other, they can broadcast their location. Based on that, you can find out the centroid of the swarm, and the centroid of the swarm you can find the radius and then say we ought to be within the radius, right. Now, the drones are free to fly anywhere in this large radius, but they are not allowed to go outside the boundary, right. So, that is very important. Why? If I detect a fire, if I want to attract someone else, I should be able to, information will give me a weightage. So, I could push the centroid towards me, so that rest of them will start coming closer and closer to the fire location, right. That is the idea. Quenching, they will be dividing the area for efficient neutralization, so that they can keep the flow rate to be constant. Lot of things are assumptions, right. Many assumptions has to be relaxed when you go into practical implementation perspective. Those are a very interesting problem for students who are attending this course. They can look at it and then try to take one other problem, try to do, so that they understand, they can apply their knowledge for these particular problems, right. Now, I make an assumption again, a fire, I know the flame length, right. I know the flame angle and I know the height of the flame. With that, I can determine what is the rate of fire spread, right. I am assuming these are measurable practically, okay. But unfortunately, in real life it is very difficult to measure the flame length because you do not know the terrain, right. So, it is difficult, but we make an assumption, we will relax one by one, right. Now, I am providing a stochastic solution. Earlier we talked about more deterministic, here more stochastic solution. The idea is simple. If I see a fire, then I have more weightage for me. My information, I see a fire, but the centroid of the drone shift towards my location, which means the entire circle will move towards me. So, it will not allow any drones to fly outside the region, right. You can ask questions, suppose what happens, two of them detects fire in both an opposite direction. The probability of the fire, right, probability of the size of the fire decides the weightage, right. If two fires are equal weightage, then they go with the random choice, right. So, what happens, I have a sensor, I have cooperative information driven search, which will detect the location of attraction, and which detect the target in location, and those informations are there. If the two UAVs comes together, then I have a global strategy. Sometime I do repel each other. So, I do not, if I am detected the fire, I am moving towards it, I do not want other swarm to come here. I try to repel that particular swarm away from me. If I see a fire larger, I am not sufficient for me to handle, then I will have a regulative merging. I will allow the other swarms comes together, we will act like a single swarm till we quench the fire. Once it is done, they will segregate and fly and on their own to search for more fire. This is the basic philosophy which we are using for divide and conquer based fire, right. Swarms are move in one direction of the maximum temperature gradient. They increase the probability of confirmation of the target. Swarm members with the maximum information, that is the one which has highest temperature gradient, that is K star. The maximum information direction is defined by the velocity of the direction of the kth swarm, and that is the direction in which the entire center shifts, and the search space will be considered towards the maximum information direction, right. So, that helps me to push the swarm towards that particular angle, heading angle, right. And then I generate a waypoint, which basically a new position which I want to follow, I will move there, right. And length of the waypoint is again depends on the probability of detection that I am going to do, and then that is what we are going to use, right. So again here we use a philosophy of what we call Oxamarina fish, right. Oxamarina fishes has a very specific nature. They just hunt as a pack. What they do, they just go for a long distance and then they do a local search there. Again they go for a long distance, they do the local search there, right. That is how they try to hunt for food. So again here, when there is no target, each swarm will have a long distance waypoint. Once they see a target, they will have a small distance waypoint to explore that region to finalize that target very effectively. That is why I said a stochastic search solution, right. And information driven, because the distance depends on the information. The angle depends on the information that what you are getting, right. So once they go into local region, they try to do Brownian, which means small step length, to search in the local space to identify the target precisely and their size. Okay. There is an attractive force within the swarm. Always swarm members moves inside the swarm boundary. Swarm members detects fire, right, preserves the swarm structure and the search space during detection. Any UAV tends to move outside the swarm. The attractive force of the swarm center pushes the UAV inside, right. Swarm member with a maximum information, right, detects the fire, and that is the direction in which rest of the members will be moving so that they can quench the fire together. This will also help the non-detected member to reach the fire faster, right. So time to reach the fire is also important, right. That is why it will help them. If they can't detect, also it will help them move closer and closer to the fire. The sensor can pick up so that they can come to the fire location and start quenching together, right. After detection, divide and conquer based rule is employed for target mitigation. Basically what happens is I sense the region, I divide the regions, right, and each swarm fly in a formation control, and they have non-overlapping regions and try to quench that particular region very effectively, right. So we can have a cooperative control here. What is the angle in which you should come, and what is the you can model the fire region as an elliptical, and then you can define the region for each one of them and then assign the task effectively, right. Approximation again, right. None of the fire region is going to be a perfect elliptical structure. You just try to approximate as close as possible. Then you can divide the regions and assign the position. What is the angular position for every member of the swarm to reach? What is the area that they need to cover, so that they have the strategy of sweeping that particular area with a constant flow rate, right. You can do that. Okay. I am not going into the math of this particular thing, it is not part of the course. I just want to give you the glimpse of what is the swarm can do, right. So group autonomy can do. Moment you finish the course, you should have an idea what kind of project that I can embark and what kind of realistic solutions where group autonomy can be used and solved. That is why I am just giving a flavor of the problem rather than going into individual mathematics is beyond the scope of this particular course. Okay. So we can try to see how such a stochastic search can do. We always do Monte Carlo simulation, putting the fire at a different locations, different number of fires, and compute how much is the area damage, what is the time to quench, what is the detection time, and then we try to see for 100 runs what is the mean point, median point, and how the different algorithms performs, and we can compare them, right. I am just giving you in a simulation sense for you to understand. There are 5 fires at different search area. They have been detected by the swarm. In some, if you notice, even the UAV flies over the fire, it will not detect. The reason is there is always a probability of detection, right. The probability of detection means it is exactly at the center is very high. But doesn't mean that even if you are at the center, you will have probability always 1. It's a random number, right? So sometimes you miss that fire also. So once you detect the fire, they start operating on the fire started quenching, right? Initially the area is decreasing, area will be small, and then once it start growing, the quench rate will, the fire will start decreasing faster and faster. If it's not detected, for example, fire 3 is not detected, it start growing bigger and bigger until some UAV detects it. Once it detects, they start quenching on it, and once they see it, they will repel the other UAV not to come to that particular point, right? So they do that task. So that's why you can see cooperative repulsion is there. So I'm able to do the task, you look for some fire. See, fire F5 is small in the beginning, it started growing higher and higher. So this repulsion allows the UAV to go and search for other fires and to mitigate, right? Now this is a stochastic solution. There could be a multiple better way of searching, right? What's a better way of searching? What is a better way of merging the two swarms together, right? So that they can effectively quench the fire, right? When the solution comes closer and closer, I can have more resources can come together, right? And they can try to quench it. In the beginning, I don't want the merging to take place. And towards the end of the endurance, I can allow people to come together and quench together, because they can quench whatever the left out fire faster and move, right? It's again a heuristic strategy. Is that the heuristic strategy is better? You can use a reinforcement learning to come up with what is a better policy of cooperative merging, so that you can quench the fire faster. You can say, I don't have to do that in the end, I can do it in the beginning also, right? What's the optimal policy that we can handle? Because this here, if you see, it's unless you quench the fire, you don't get a reward. Unless you detect the fire, you don't get any reward. So it's a sparse reward problem, right? So what is the optimal policy needed? All these are very interesting problems for those who are interested to apply group autonomy, right? Moving from this course where you can go. That's the objective of this particular lecture on swarm, right? Think about it. There are a lot of such interesting problems where multiple UAV can come together and work together, cooperation, coordination, all these are very interesting aspects of group autonomy, right? In summary, learning based solutions helps the cooperation, collaboration in swarm better. The learning based solutions can handle the sensor uncertainty, decision making uncertainty, and communication uncertainty, right? And the decentralized way to go about. But whatever we have demonstrated here is not learning based solutions, right? They are just having a predefined fixed strategy, right? Heuristic. So one can look at how we can bring in so that we can handle if the targets are agile. If the targets, if the wavefronts are not known, how do we do it, right? So those kind of things, when you talk about task, is different, right? There could be a lot of single robot tasks, there could be a lot of multi-robot tasks. Now what the swarm will do? Will it take the single robot task or will it take the multi-robot task? If I do a multi-robot task, I need a coordination. I have to pay some price for communication. If I take a single robot task, I don't have to pay price for communication, but it comes with the challenge. The multi-robot task will start growing faster and faster because they spread faster and faster, become bigger and bigger. And they create rate of damage is much higher than the single robot task. It's like a conflict, right? It's a multi-objective optimization framework. How do we do that? How do we combine with the best strategy so that the multiple UAVs within the swarm can handle the task more effectively, right? I talked about single large fire. There could be always clusters of fire within the radius. How are you going to handle? Right? A suddenly small wind can just take fire from one location to another location. There will be a small clusters of fire. How am I going to handle this? Because I don't know the number of tasks and how this spot fire is going to come up, right? So these are very interesting problems where swarm of UAV plays an important role, right. On top of it you can add in constraints like I have a limited capacity. When I have a limited capacity I cannot quench for infinite time. I have to go for refueling and come back, right. That time will also play an important role. So you can look at various problems where real life problems where a group of UAV can come together and solve, right. So we thought this could just open the door for students who are taking this particular course to think about applications beyond single UAV, right. Thank you so much.